Good afternoon, everyone. Thank you for joining our call. We still have people joining, but we will kick things off as it's just after 4 p.m. My name is Sue Davies, and I work at STFC, Science and Technology Facilities Council, as part of the Business Innovation Directorate. And I am your host for this session. Just to give you a little bit of information regarding our Zoom etiquette. You'll all note that you are all on mute, so please ensure your audio is muted. For the Q&A session, we will direct all questions via the chat function. So if you can, while the speakers are speaking and have a question, pop it into the chat at the bottom of your screen here. And we will answer the questions as much as possible towards the end of the session. If you experience any technical issues, then please log off and log back on again. Hopefully we won't, but just in case. And audio and presentations, we will be recording this session, and it will be available afterwards. And the presentations, you can have access to the presentations. So just request them from us and we can send them to you. Okay, so I'm going to stop sharing now, and I will pass over to Nick Trigg, who is head of the Astropreneur program. Nick.
Good afternoon, everybody. Hello and welcome to the fourth in our series of Space Plus One talks. Is my slide up? Yeah, this is our fourth in our spring-summer series of Space Plus One. This is where we try and get experts from outside space or even inside space to talk to you about related subjects that we think you might find interesting. So in the past three series events, we've concentrated on downstream topics. So we had talks on space technologies used in agriculture, sustainable finance, and government. Those are available if you're interested. And next week we have Orbits, an introduction, or Orbits 101. So that's on Tuesday at 10. I'll put the link in the chat if you're interested in joining in for those. So today we have manufacturing for space and robotics in challenging environments. And the speakers today are Mike Curtis Rouse, who's head of manufacturing at the Satellite Applications Catapult, and Rob Buckingham, who's CEO at RACE, which is UK AEA. Just a quick word on the Astropreneurs program before we pass to Rob. It's a Horizon 2020 funded project supporting space-related startups with mentoring and training, the objective of which is to support and train the entrepreneurs, early career entrepreneurs, and support businesses so that they grow to more profitable position. The partners in the program are scattered around Europe. There are 8 in total. The leader is Instituto Pedro Nunes in Portugal. But if you're interested in talking about the program, obviously you can talk to any of the partner businesses. And it supports businesses and startups throughout the whole 28 countries of Europe, not just those partner countries. The information is available at astropreneurs.eu. It surprised this mentoring and training to these startups for a period of up to about 6 months. Those companies just need to have a space connection, and any space connection will do, upstream, downstream, hardware, software, anything you like. And it is early stage, so you can even be pre-incorporation or obviously post as well. The program to date is supporting 160 approximately entrepreneurs across the Euro 28 countries, and it's split across a variety of upstream down software companies and across the whole range of industry sectors. Thank you very much indeed. I will now pass over to, is Mike around, or am I passing to Rob? I think I'll stop sharing, and Rob, if you can go.
Good. Can you see that?
You can.
Yes, we can.
Excellent. Hello, everybody. As Leonard Cohen said, it's wonderful to be gathered here on just the other side of intimacy. I'm Rob Buckingham. I'm the a director of the Atomic Energy Authority, and I head up part of the UK AEA at Culham called the Remote Applications and in Challenging Environments, the Centre for Remote Applications in Challenging Environments. And I'm going to talk to you about some of the work that we're doing at Culham in relation mostly to JET, the Joint European Torus, and how we maintain it, how we remotely operate and maintain it. And the general theme of the talk is design for X, where in this case X is remote. And this is clearly a challenge that we're going to face both in the nuclear sector and space sector. So UKA's race. We're a government-run organisation, so we're largely still government-funded, but we do a lot of collaboration with other people. There's a few stats, and the picture on the right of the facility. It's about 100. Well, it's about 200 people now. Still growing. 20 vacancies. Lots of projects. I did a tally just recently about £345 million of projects that we're involved with. That's not stuff we're doing. That's just projects. That's the total project value. Our activity is about 15 million per annum in terms of OPEX, and then a whole load of hardware on top. So lots of collaboration with industrial partners and university partners. Now, the reason we exist, the authority's mission, the Atomic Energy Authority's mission is fusion. That crazy thing that if we made it happen, it would change the world and change humanity. From a robotics perspective, I'm a roboticist by background. From a robotics perspective, it represents pretty much the most challenging thing that we're trying to do as engineers on the planet. It's a really hazardous, harsh environment, extreme levels of radiation, extreme temperature, residual magnetism, vacuum, and all of the access problems that come with a really complicated piece of kit. And that means that remote operations and maintenance is device defining. It means to say we have to look at the design of this whole thing through the lens of remote ops. Otherwise, we will design something that will never be able to be maintained. So I'm going to talk quite a bit about JET, and that's JET in its shutdown state. You'll see this picture a little bit later on. But basically, this is showing it with two yellow robots that look like sort of bendy chopsticks, and they reach inside the torus and do the work, and people operate these machines remotely. So quick introduction to JET. It's been running for quite a few years, quite a few decades now over at Culham. And we've been doing the remote ops for about 25 years. So RACE maintains, develops, operates all the equipment. So 35,000 hours of in-vessel operations and about the same sort of thing outside. Two articulated booms, lots of haptics. I'll talk about the importance of force feedback when you're doing assembly and reassembly. Fully remote operations, so we're just building up to a shutdown where we will not be allowed at all to let people inside the reactor vessel itself. And vast amounts of information, loads of tasks. I've 143 detailed task descriptions. These are really detailed task descriptions, 951 bespoke tools for interacting with the environment, and 1.5 million actions logged. So this hopefully will run. It's a quick video. I'll show you a bit of it. This is JET on the outside. That's JET on the inside. That's the picture I just showed you with the two robots. I call them the surgeon and the scrub nurse. This is just a quick run through how JET has changed over the years. And this is one of the challenges with these expensive pieces of kit and things that might be in space. Will they stay the same or will they change? How will they need to be updated and maintained through their lives? JET certainly would have been shut down had it not been for the ability to go in there and change stuff. And so we changed stuff inside the reactor using these two big booms, as we call them. These are big robot arms that reach in. And these robot arms carry two things. One of them carries a chest of drawers, some shelves, and the other carries that thing there, which is a bi-arm manipulator. and that biomanipulator is able to feel the force that is being exerted at the other end. And then there's a whole load of tools, as I said, 900 and something odd tools that are used and are designed to do a lot of things inside the reactor. So when you start thinking about what needs to be done inside a space as seemingly simple as JET, but actually it's really quite complicated. But there are more complicated spaces than the inside of JET. But when you start thinking about what needs to be done inside there, you start to draw up a very long list. And it's all the boring stuff that people would normally do if they were able to get inside. The handling, the bolting, the cutting, the welding, you know, you can read the list. And you can add another 50 odd tasks to that without any difficulty at all. And we have replaced the whole of the inside of JET remotely. That was about 4,000 components out and 4,000 components back in, and it worked at the end of it. And that's really rather important. I'll come back to the issue about actually the challenge here is reassembly. It's not first assembly, it's not even first dismantling, it's reassembly to make something work after you've made changes. So let's run through a few of the components. I am going to go into detail because we can talk generalities perhaps in the Q&A, but I'm going to sort of talk about what's going on in practice to give you a sense of, you know, the engineering. It's loads of pictures. So those of you who are not engineers, don't worry. So basically, you've got hands, you've got two grippers, and they're pretty simplistic. And we've gone for very simple grippers so that we can interact with many things by defining the interfaces on the tools that we then hold with this simple gripper. So that gripper sits on the end of two arms, and the two arms are sort of shaped a bit like, well, they have the same kinematics, the same structure as human arms. So a person is driving the arms. In fact, the picture behind me, if I lean the other way, is the JET remote ops control room. So you see Justin there at the controls of the master that controls the slave on the screen. And so the driver is feeling what is going on at the other end. So just like you can, you know, see digitally with a camera and a TV, this is feeling digitally with a sensor and then a device which is putting the forces into your fingers, which you then obviously feel. So it's the equivalent of, you know, a TV system, but in the force spectrum. So there are lots of constraints on what we're allowed to do inside this space. This is one of them. This is our tool chest that we're able to take in. So that's our lunch. Let's call it that. You know, if you've got a packed lunch, you've got a banana and an apple, and they're in the tray, and that's it. So you can think about the logistics of making sure the right things are in the right place so that when we're in there, we've got the right tools. And of course, you've got to bring it all out again. That's why I describe this as, you know, surgeon and scrub nurse. So one of the things you want to do is make sure you're ready, and you also don't want to leave anything behind when you come out. And this is another constraint. So that's the outside of the JET vessel. So that's the thing that has the fusion going on inside it. And it's a torus, it's a ring donut. And that's the port. So that's the hole that we have to get everything through. And that means to say that we do have to be rather careful with the design of stuff that goes inside. So things that go inside, the one on the left, that's a wire brush on the end of a golden fixture. The golden fixture is rather clever. It looks simple, but that's a key issue here. And then there's a wire brush stuck on the end of it. And the one on the right is actually it's a bandsaw. So a much more complicated machine that is going to cut through some bits that we had to remove, and it has vacuum attached to it and things like that to collect the swarf. And so those are, you know, the range of tools that you have to get into an environment like this. And you've got to think about how the arms will actually deliver that. So where is the mass? Where's the center of gravity? All that normal stuff. Just like, you know, if you're doing a task in the kitchen or in the garden at the moment, you know, you're positioning yourself so that the forces are all okay. And you're handling some complicated things, so you've got to think very carefully about the size of them, the rigidity of them, how you interact with them, the tools that you're going to need. So that's an example there on the left of a measurement fixture, actually, which is installed and used to do a load of setting up inside the reactor. We do a lot of stuff in digital. Digital technology is coming on leaps and bounds, and again, the picture behind me shows a load of different views that we create of the inside of the reactor, and those could be cameras views or CAD views, and increasingly we're seeing the amalgamation of these views and augmented reality and virtual reality and all that stuff that you'll have heard about, no doubt. And then practically, so this is not a games engine. Well, actually, it is drawing on the tech that comes from games, but it's not for gaming. We really do need to know exactly where everything is and what's going on. So things like what the cameras are looking at and what the lines of sight are really important, so that you can gauge how to assemble. So the level of detail that goes into planning remote ops is extreme, and that's perhaps one of the biggest, most obvious differences. Humans would jump into a space like this and just get on with it, and you'd say, take that off the wall, and all of those words would mean something, and the person would just get on with it. But in this environment, we have to be very prescriptive. And we could talk about how we're going to get less prescriptive with time as we use more autonomy and artificial intelligence and things like that. But that's one of the challenges here. We have to be really quite prescriptive about what happens. I've gone the wrong way. So down to the detail rather. We do all sorts of things like making sure we use consistent colors for different components, for where we're going to interact with parts, and the layout of each part is very carefully considered for how we're going to interact with it. So you see more of these golden fixtures. They're designed so that that two-finger grip can grab hold of these things very precisely, easily, fast. We're very interested in speed, and also they've got fixtures which lock into the fingers so that you can't drop them. And actually, you've got a foot pedal to allow them to be released, because of course dropping something inside jet would be bad. And when you're using two hands, you've got to make sure that the grip's in the right place so you can actually do the transfer. So it's a bit like a Rubik's Cube. You're letting go and grabbing in different ways so that you can interact with parts as efficiently as possible. And interfaces to components are really important. And we've done a lot of work on these dowels, which allow you to engage components without things being damaged in a way that sort of takes away the degrees of freedom. You go from complete freedom of movement to fixed in a very easy and simple way. So they look simple, and indeed they are. That's the intention, is to simplify everything so that it works as cleanly and as fast as possible. Little things, it's just simple things. We've got indicators on stuff to say it's okay. And lots of other features. So for instance, I'll pick up one of those. We got all of our bolts, which you would, you don't want to go and drop a bolt. How many times have you built something at home and dropped a bolt? Oh, it happens all the time. So, captivated bolts, and you release the bolt and it doesn't ping off. They're held in the right place and you're ready. Things are in the right place, but you can see that every single little feature of these tools has been considered from the perspective of how it's going to work inside the reactor. This is another quick example. This is a bolt runner, and it's got three functions. You can use it as a sort of a fixed Allen key, and then you've got a ratchet going backwards or forwards, and you can select how the gripper engages with that tool to do those things. And it takes minutes off tasks, but when you've got hundreds of tasks, then that's lots and lots of minutes. Failure is probably the most, and I'm just going to turn off my phone. Sorry about that. Big mistake on a webinar. So failure is a really important thing. It actually, the bottom point there, recovery from failure is the real design challenge, is perhaps one of the statements that And now the home phone is ringing. Such is life. The I'm a man in need. Yes, something like that. So recovery from failure is the real design challenge for all remote ops. You have to design things with the idea that something's going to fail. So when we're running through all of the processes that would be involved in a remote operations campaign, we are often thinking about what happens if we stopped here? What would happen if something broke right here, right now? How would we recover from it? And that is a deeply challenging test for any type of engineering system. And there's a whole process that we go through, and I'm going to rattle through this very rapidly. So you're capturing the requirements, you do a lot of stuff in digital, then you mock things up, then you're doing the final design, manufacture, and then use in vessels. So there's a long process to get to a point where things actually can be released into the wild. So I mentioned about the virtual reality stuff, and there's an amazing amount that's going on in the games world that is going to be appropriate and relevant to speed things up, especially with the strategy management and bringing in different stakeholders. And I include stakeholders like regulators, the government, even the public. If you want to show people what's going on inside Jet, then actually VR is a great way of doing that. Then there's physical mock-ups as well, and we do little things like that. And then this one is our full-scale Death Star. So that's full-scale Jet. That the greenish bit in the middle is actually the 9th octant of Jet. It was a spare, and we use that spare as a test environment, and we do all sorts of prep work inside that space. And I'll pick up on one point on here in particular. Training is really key. So again, using that medical analogy, you wouldn't want a surgeon to just leap in and start practicing on you. And you also want that surgeon to be kept at a certain level of performance. And the same is true for us. We invest a huge amount of money to make sure that our operators at all levels are up to scratch and able to work in effective teams. We have a number of teams, a number of shifts that will work, 2 or 3 shifts a day, and we're switching around between the teams to ensure that that the team members are really professional in the way that they're able to interact with each other. So that training piece is absolutely critical. We do more and more of it in the VR side of things, and then finish it off nowadays in the physical mock-ups. And then there's a whole back end. So identification, you could have called that anything, data management, but clearly there's a big logistics piece around all the tools and where they are and what condition they're in and all of that. And the side that goes with this, and this is actually where I'm going to stop, is it's around the operations management. So we script the activities that happen within the reactor. We take a great deal of time to ensure that people don't take shortcuts, that they talk, that they're working through a pre-agreed process, and that the team of people that are working know where they're at in the process, and they're checking each other. So there's a lot of teamwork that's going on around this to make sure that the final goal is reached. What's next? So the 2 drivers that we've got is, the first one is increased productivity, and the second one is, ideally we would like better design tools. So we want an enhanced design tool, and by increased productivity, really that just means moving faster. So more automation, taking people out of the loop, so more autonomy, more machine learning for the tricky stuff. But what we do know is, putting a bolt in and avoiding it actually getting jammed is really quite tricky. And we have had many occasions where, not many, we've had a number of occasions where we've actually had to drill out bolts that have got jammed, and that is really rather complicated using remote operated tools. So that's recovery from failure. So the photorealism is coming, but actually I'm interested in much more than that. And really what we're doing is augmenting the photorealistic bit with force realism, with sensor data, with condition monitoring, and also know-how. I've called it know-how because it's all the other human information that we would like available as we're going through a task, so that we know where we are and what's going on and what's coming next. And we want also to really integrate the operational management piece with all of these tools, so that actually we can do more of it online, and we can run through things in a virtual space. And then the enhanced design tool, so D4S, a design for service, that's sort of what the aerospace sector calls this, and I suspect that's probably the title, the phrase which should be used for all of this. Design for service is going to become a key lens from which we actually look at at the concept of viability. Is in this case the fusion reactor a viable design? What are its implications? What are the implications for operating and maintaining it over months, years, and much more? And as I started with at the very beginning, a really big test is actually, this is designed for reassembly. So assembly is quite easy. You know, things are, you know, coming out of manufactured, they're manufactured clean, they're tidy, no damage. After you spend a bit of time inside a fusion reactor, you're a bit knocked about. So, you know, taking things apart and then reassembling them in a form which they then work is a truly demanding task. Hence, we need design for service. And there I'll leave you. And I suppose the question that I wanted to ask, and one of the reasons why I volunteered to talk, is actually design for service is going to become increasingly important in many, many sectors. And space and nuclear are the ones that are probably going to lead, certainly the leading pack, because of the challenges associated with those environments. So maybe there's something here in combination where actually space and nuclear should be working together to think about how you design the next generation of device in space or fusion device. Thanks very much.
Thank you, Rob. Okay, we will move on to the pitches now.
Mike is here.
Oh, okay. Sorry, we'll go on to Mike. Mike, if you can start sharing your screen, please.
You're on mute, Mike, yeah.
I know.
Great.
Good. Right. Good afternoon, everybody. Apologies for my slightly late arrival to this. I'm Mike Kitterstrauss. I'm Head of Manufacturing for Space at the Satellite Catapult. And this is just going to be a relatively quick whiz through what we're terming as the next Wild West for space. So when we talk about manufacturing in space, there are always an awful lot of aspirations about what it could be. Now, the reality is manufacturing in space is a new market, and it's certainly, there are new approaches to manufacturing, and potentially in the long term there might be new worlds. But I can assure you that we're not going to be seeing any activity like this probably for the next decade, if not 3 decades. So any ideas in terms of mass construction of giant mirrors and very large frameworks, etc., in space, by people, or by, in this case, it looks like these are some form of exoskeleton, etc., of people assembling platforms, is going to be highly unlikely. So what is the reality? Well, the reality is probably slightly more mundane, but equally still probably quite exciting. So if we look around where the opportunities are, fundamentally for manufacturing space, it's about assembling technology. And Rob's been talking about in the previous presentation about using robotics, using autonomy, and using tooling, etc., to build complex objects. Building a fusion reactor, I would argue, is probably in some respects harder to build on Earth than it is to do much of the assembly we've done in space so far. Nonetheless, if we want to build larger structures, we want to build more complex structures, then we're going to need a high degree of robotics and a high degree of autonomy. Fundamentally, though, assembly in space is one of the main reasons for doing manufacturing in space, but it's not the only reason. There are other activities which can happen in space where manufacturing is key, and that's enabling a whole variety of new opportunities. So we're seeing effectively what is a transition from in-space activities, so effectively the elements on the left-hand side. So what do we do in space currently from a commercial perspective? Well, if we ignore the space station, which in some ways is a misnomer, because the space station is very much a curiosity, science-driven platform, If we look at the commercial activities which are physically happening in space, then we're looking at a combination of Earth observation, satellite communications, navigation and positioning systems. These are the systems that we are fundamentally using for commercial activities, and we are using to drive the commercial model. But what are the other opportunities? Well, the other opportunities are doing things physically in space, creating this commercial environment where instead of just doing science-based curiosity and science-driven experimentation, we're now looking to utilize the space environment to manufacture a variety of products. And these can be materials, these can be using platforms which expose biological substances and processes to the hard vacuum of space, or we can be using platforms for observing actions of processes, so formations of alloys, formations of ceramics, physically utilizing the space environment and using space stations and perhaps other platforms to do so. Now, one of the interesting facts is, which is partially driving this, this is a list of a database that I and others maintain of launch vehicle companies. Now, when I say launch vehicle, I mean spaceplane, I mean rocket, or something along those lines. There are other flavors: air launch, balloon, spin launch in California are building a giant catapult, nothing to do with this catapult. They're firmly on their own in that respect. But there's a whole variety of different technologies out there. What's fascinating though is in 2005, there were about 12 launch vehicle companies. Last year, globally, there were suddenly 196. This year, irrespective of COVID, we're now at 248. Now, a large proportion of these launch vehicle companies are much more slideware than they are hardware, but they still perpetrate to exist. They still are talking about building launch vehicles in some capacity. Many of these are Chinese state-sponsored, so you can comfortably take at least 2 dozen, perhaps 3 dozen of these companies and wrap them up in such a way that you would consider them to be broadly all of the same parent organization. And you can do similar activities to an extent also for Russia and a few other countries. But for the most part, you've probably got something in the region of about 190 bona fide independent companies building things. And that's pretty significant in the scheme of things. So what does that mean? Well, that means fundamentally we've got new ways of getting things into space. When we think launch, we're no longer just thinking purely about the newcomers in terms of SpaceX, not that SpaceX is probably a newcomer anymore in the scheme of things, or we're talking about Rocket Lab, or we're talking about Firefly. We're now looking at some of these newer companies. In the UK, for example, we have Orbex, who are a Danish-UK company expecting to start launching out of Scotland in about 18 months' time. We have other companies like Skyrora operating in Edinburgh, expecting to launch in probably 2 years' time. And then there are organizations like Small Smart Systems in Wales, Dragon Aerospace, B2 Space, and many others. And those are just some of the ones in the UK. So suddenly there's this greater lift capability, the ability to put more things into space. And if we can put more things into space, we can do more things in space. So making things in space isn't fundamentally new though. You know, there's significant precedents. We're not talking about, when we say making things in space, as this is a brand new activity. If we go back as far as activities, for example, such as Skylab, one of the early American space stations, effectively Mir, the effectively subsequent Russian space station, of which one of the first UK astronauts, Helen Sharman, flew on. Later on, effectively, apologies, back to front, you can see what's left of the International Space Station in the background. Massive construction activities, and recently with contracts as recently placed as early as today with Northrop Grumman, activities for the Gateway space station, which is the next big space station to be built, which will be built in orbit of the Earth and then will effectively be assembled and moved fully in orbit of the Moon. And this will act as basically, as it says, physically, a gateway to Luna, a gateway to act as a refueling station, etc. And you can see there's similarities in this configuration to that of the space station, built out of modules, assembled, but the technology here will be increasingly more robotic, will be more manufacturing driven. But the aspiration is to do more. This is assembly of big structures. The aspiration is to build larger, complex objects, but equally smaller complex objects, which we can utilize the benefits of space for. So going into perhaps smaller detail, Made in Space, a US company who are playing with a variety of flavors of additive manufacturing, have for a while been touting their wares in terms of This is fused deposition modeling. Basically, it's a 3D printer in space. Now, the reality of making tools in space is probably not actually as useful as it sounds. An awful lot of tools you take with you, and yes, there's always a risk of losing tools, and you can only ultimately print a tool as fast as you can use one, or perhaps arguably lose one. But some of the material properties, this is effectively a ratchet. The reality is the tensile strength of that ratchet is pretty limited. You're not going to be using that to tighten bolts on the external hull of the space station, but you might be manufacturing a variety of other things at the same time. So if we're looking at industrial manufacturing processes, we can do a whole variety of different things in space using the space environment. So for a start, one which is generally assumed, why would we do things in space? One of those fundamental things is effectively removing the effect of gravity. Now, actually, this is not so much removing the effect of gravity. Gravity is still prevalent, it's just smaller. So we're in a microgravity environment. And microgravity allows materials to mix together. It allows them to mix evenly, so we can create homogeneous structures, and we can do it effectively without the need for traditional supports. So that allows you to build complex scaffolds. It allows you to work with a variety of metals and creating different types of alloys, different types of ceramics, and different types of plastics. At the same time, being able to utilize an ultra-high vacuum allows you to form things without impurities. And that can be anything from semiconductors to ultra-pure forms of alloys. And there's a variety of companies operating in this space. As I said earlier, the ubiquitous one is made in space, but most of the space agencies are operating here at a relatively high precedence, as well as organizations like Airbus and General Electric showing interest in the potential of what can you do physically in space. From a biological perspective, however, there's an even wider series of benefits. So microgravity gives you a whole series of advantages, everything ranging from no scaffolding needing for 3D biostructures, no solute buildup, no buoyancy, no phase separation, no wetting. It allows you to do faster cellular growth. You can model effectively accelerated bone and muscle loss. You can look at different ways of doing crystallization and combustion. So there's an awful lot of companies here engaging already in this effectively environment, seeing potentially commercially benefits here from where they can exploit processes like protein crystallization, 3D bioprinting, which is broadly a spin on conventional 3D printing for industrial materials, cell cultivation. I mentioned accelerated disease modeling, which you can do for effectively muscle and bone. Microencapsulation, which is a process which has been happening since the days of the space shuttle, applicable to biological, but also applicable to more industrial processes, nanofluidics and biofilms. And biofilms, again, and nanofluidics are sharing effectively potential with other industrial processes for semiconductor manufacture, thin film deposition, the ability to make ultra pure, ultra high efficiency solar panels. And the benefit of being able to do processes like that is that we can then start to manufacture components on orbit, which we can use in orbit. Not necessarily.
Be gone, Feldon.
It's very confusing. It's happening. Okay, I shall continue. The noise has disappeared.
Go ahead, Mike.
Thank you. I was a little confused what was going on. One of the examples of this actually physically happening today is something called ZBLAN. And ZBLAN is a type of fluoride-based optical fiber that has a potential to perform more than 100 times more efficiently than a traditional silica-based fiber. And this is because when you manufacture this optical fiber in microgravity, you end up with minimal impurities, where on Earth, the gravity-driven forces result in a higher degree of impurity in the fibers. In space, you can manufacture this fiber. Thus far, Made in Space and other companies who are trying to do this haven't managed to successfully make more than a few meters worth of optical fiber. The reality is if you actually want to use this fiber in meaningful environments, etc., you'd need to manufacture realistically tens, if not hundreds, preferably potentially thousands of meters of fiber. But the benefit of it, because of this ultra high performance, is the ability then to use it in a whole variety of different industries. Everything from medical devices like laser scalpels to sub-oceanic telecommunications. And there's a variety of ways to do this. One of the really interesting things about effectively ZBLAN is, or any other optical fibers, you don't need to lift a lot of mass in order to make a lot of material. So taking effectively a glass ingot to orbit, which might weigh 4 to 5 kilos, can produce a phenomenal amount of optical fiber. So effectively, the mass to effectively profit ratio is very good. So in terms of manufacturing, there's a whole variety of different systems currently being tried on the space station. These are all some of the examples of platforms which are being used currently in space on the space station to manufacture. And the best example is probably the middle one from the Physical Optics Corporation, where you can see the wheel on the left-hand side is going to basically extrude that optical fiber from the ingot at a high temperature. So effectively you're extracting that and then spinning it around the wheel. The problem with all of these systems, as I've said, is the ability to manufacture the fiber in long lengths. Thus far, for most of the time, no one's managed to manufacture more than a few tens of meters at the most. However, this is very much quite a fundamental space station way of doing it, with astronauts who are ultra-trained engineers with a degree of curiosity, which can be a good thing or equally a bad thing, but on the space station. The going rate roughly for an astronaut per hour is somewhere in the region between $17,000 to $22,000 an hour. So you can see very rapidly the ability to actually manufacture something and make a nominal commercial return on it, if your labor is costing you $22,000 an hour, is going to be fairly slim. So ultimately, what needs to happen is there needs to be a potential transition to more automation. And this ultimately was going to overlap with some of the areas that Rob was touching on earlier. So ideally what you'd be looking for would be some form of effectively free-flying autonomous factory. So this avoids all the limitations that you would have potentially using the ISS, i.e. you don't have astronauts. This is an automated process. This effectively factory would fly. At some point it will be docked upon with a return to Earth vehicle, which would probably bring up material at the same time as collecting material and bringing that back down to Earth. You remove the need for astronauts, you remove the need for all the life support and all the complexity, and you're probably going to build this around probably one of the existing human-rated transfer vehicles. So for example, the Crew Dragon, which flew a couple of weeks ago to the space station, might be a good model to build it upon. But equally, Europe and other parts of the world have expertise in terms of the autonomous transfer vehicles, Cygnus in terms of resupply, the ISS, etc. So there's a lot of precedence in terms of how we could build a free-flying factory. Where would we go beyond that? Well, ultimately, there's the cislunar economy, and this is really where it gets exciting. And whether this happens certainly in some of our lifetimes is debatable, but I'm sure that for some of the audience on this call, this potentially will happen in your lifetime. So already we're seeing the Gateway Station being contracted out and ready to be built at the Lagrange 1 point for the Moon. We're already seeing activities on LEO, in GEO for manufacturing and assembly. The ISS is built and more or less complete, and we're beginning to see the future opportunities for lifetime extension, etc., of the ISS, be that commercial or otherwise. Organisations like the UK Space Agency and others are beginning to look at opportunities around solar power stations, where we can basically have 3 or 4 power stations on orbit, 5 to 10 gigawatts each, which will effectively provide the entirety of the UK's electrical energy supply. If we're going to build such structures, we're going to need manufacturing and assembly technologies, some of which I've detailed, others which will need to be developed. The more ambitious activities are those which involve material harvesting and in-situ utilisation, going out to near-Earth objects like asteroids, identifying materials we can utilise, not gold, not diamond, because they're not particularly useful, but materials like aluminium, steels, titaniums, the materials that we use extensively in space, and more critically so, ice, which we can use both for water, we can create oxygen, and of course we can also use it for propulsion. So a whole fundamental, effectively ecosystem which exists around the Earth and beyond the Earth. Ladies and gentlemen, thank you for listening. That's my final slide. Thank you.
Thank you, Mike. Next we have Simon, Simon Evans. Simon, can you please start sharing your slides?
Will do. Thank you, Sue. Bear with me. So hopefully you can see my first slide. And Nick, Sue, thank you very much for giving me the opportunity to present BlueBIS today. BlueBIS is establishing a multi-sector research, test and training centre, the first in the UK, centred around the world's largest pool, primarily to support the offshore energy, maritime, defence and space sectors. Let me get on to our next slide. This extreme environment facility is designed to reduce the cost of and enhance the capacity for the human procedural and technological innovation required to expand maritime, that's energy and defense, and space, research, education, and industrial activity. We'll offer simulated environments with state-of-the-art support workshops and ancillaries, with cutting-edge technology incorporating virtual, augmented, and mixed reality, and advanced console monitoring and training simulation capabilities. We'll also offer challenging environments, including hyperbaric and high and low gravity, with nearby access to open water and offshore locations, and the ability to stress technology to assess resilience, performance, and lifespan. We are building Blue Abyss because there is a subsea infrastructure gap in Western Europe and in certain other regions of the world. UK competitiveness will be enhanced by having appropriate and accessible subsea technology development infrastructure within our shores. And then there is the emerging commercial human spaceflight sector. Currently, there does not exist complete commercial services and facilities for the end-to-end preparation of people and technology for space. Blue Abyss will be able to train the thousands of people who will be going into space in the years ahead. So by establishing a facility that can support and facilitate innovation in the fields of subsea and space technology and operational procedures, Blue Abyss will enhance progress within multiple strategically important sectors with aligned needs. And a number of secondary markets are also served, some of which are priority fields of endeavour. As I speak, we're in the final stages of negotiations for where Blue Abyss will be located in the UK. And we know that the build phase will be approximately 18 to 24 months, so that hopefully will be operational in 2022. So we welcome the opportunity to talk to any potential partners, any collaborators, clients, or investors. Thank you very much for your attention. And Sue, I'll pass back to you.
Thank you very much. Next up, we have Joshua from SpaceForge. Joshua, are you ready to share your slides?
Yeah, hello. Okay, hopefully that's working for everyone. So hi there, my name is Josh Weston. I'm CEO and co-founder of SpaceForge.
Can you put it onto your presentation mode, please, Joshua?
Does that work?
On full screen.
There we are.
Yeah, perfect. Thank you.
Sorry, clicked on the wrong window. So thank you very much for your time. SpaceForge, we co-founded back in 2018, largely with the sole ambition of addressing, to be honest, many of the gaps that Mike Curtis mentioned in his presentation, which is the ability to manufacture at scale on orbit, specifically for the return to Earth. Our primary focus is really driving forward the next generation of sustainability from space, and as we see it, leading and enabling the clean industrial revolution. So at SpaceForge, what we've done is we found a way to enable the sustainable use of the space environment. So we do that by accessing all the things that allow it to overcome the barriers to manufacturing on Earth, so that's chiefly gravity, pressure, and temperature, all of which you can access much better variants or wider variants of in space. Now, the way that we are doing this sustainably is we have developed a fully recoverable, reusable, and recyclable satellite platform. This is specifically to build on the success of the International Space Station, which has been a fantastic tool for the basis of many of the commercial applications for manufacturing in space, but it's simply not the best place to go. And that's primarily because it's not a factory. Astronauts have, 101 other tasks to do. The orbit that it sort of inhabits is fairly contaminated because the structure itself is leaky. Every time an astronaut touches a panel, it disturbs the microgravity environment. And if you're trying to do something that's entirely novel on the space station, then it might take you 3 to 5 years to have that process approved. So actually what you can do is you can move away from the space station with a free flyer such as ours, and you can access all of those benefits much more reliably and quickly. Now, importantly, we're not the first people to do this. So this is a GIF, I'm hoping it's working for you all, from what was called, unfortunately now, Project Corona. Now, Project Corona was back in the 60s and it ran until the mid-80s. This was how America basically conducted its reconnaissance in Russia. And what it did was it flew what's called a keyhole satellite. It looks a bit like a rocket over the Soviet Union, where it had a film camera. It would take loads of pictures, click, click, click. And as it returned back over the Pacific near Hawaii, it would drop this film canister from space. And it would descend at about 60 meters a second until it reached sort of 20 kilometers altitude and lower, where 5 pilots would be waiting to try and collect the canister as it fell. Now, the training cost for those pilots was $100 million in 1960s money. And you had to have a 98% success rate in order to make the cut for the team. And it took 5 pilots, each in their own C-130. You then had 2 air-to-air refueling craft. You had fast jets for reconnaissance and spotting that nobody else was going to try and take it, a support helicopter and a support ship.
Josh, 3 minutes, Josh.
Oh, okay. Well, there we are then. So
if you can wrap it up quickly. Thank you.
Yeah. So just to say then that we've
so sorry. Yeah. Finish.
Yeah. Shall I finish?
Yeah. Sorry. Yeah.
Yeah.
Go ahead.
Okay. So just to say that we've taken that technology for the 21st century, and basically we've been able to leverage the last 50 or so years of technology development. And I'm pleased to say that we've got the Forgestar 1. The first flight of this is ready for the end of next year. This will be our first fully returnable satellite platform. And yeah, happy to talk to anybody who'd be interested in partnering on the manufacturing side of things, the supply chain, the operations, and the return and recovery. Thank you.
Thank you, Josh. Okay, if you can stop sharing your screen, please. Thank you very much. Okay, we have some questions from the audience, so thank you very much for that. The first question is task planning in JET, J-E-T. Is this the same as task planning and tool control for a space operation? I think maybe that should go to Rob, maybe?
Yes, is the simple answer. It's you can call it what you like. It's getting organized so that you know what you're up to.
Thank you. Next question. If we have to design an annular linear induction pumps for a space reactor, can we do it remotely, or does it require minimalistic supervision? Maybe Rob, can you answer that question?
An annular linear induction for a space reactor, can we do it remotely, or does it require minimalistic? I'm going to hand that to anybody else.
Depends on the type of reactor.
Perhaps Mike.
Reactor. I mean, Rob, that's kind of half you, half me. Can we build a fusion reactor, if that is a question, not a semiconductor reactor on orbit, autonomously? Yes. How long would it take us? A very long time.
Yeah, I'll just pick up on that. It's the building of these things. We've got some weird feedback, sorry, on the line. Don't underestimate what people do and make it look really simple compared to how things can actually work if you've got when you start putting robots in the loops, things start slowing down a lot.
Okay, thank you.
Back to you, Sue.
Is there any US company lists, launch vehicle companies, say?
No, there's a series of people like me around the world who maintain various lists of the sane companies, the lunatic companies, and the ones who are frankly completely mad. but there's not generally a list you can actually by de facto go to. I'm quite happy to share the details I have, so if anyone who has an interest there wants to contact me either on LinkedIn or via my email address, I'll be happy to share.
Thank you. Can we develop technology to produce fuel storage cells completely into space?
Well, we certainly can develop the technology. If we were going to manufacture the fuel cells on orbit, there'd have to be a good reason to do so, because proton exchange membrane or an equivalent, they're hard to make on Earth, but you certainly could.
Thank you. Is there any way we can build a multi-story radioisotope thermoelectric generator completely in a space microgravity environment?
Well, kind of like the linear reactor, there's many of these things we could do. The question is whether we would have the commercial case to do it. So most of the building things in space is not fundamentally hard per se. It's actually harder to build things at the bottom of the ocean than it is in space. But the number of lifts you would need to do in terms of launch vehicles, the subsequent assembly, and the experience we would need to gain would be exceptionally challenging. There's no reason to prohibit us, for example, potentially building an O'Neill cylinder, which is a multi-kilometer long rotating cylinder, in which case you generate a degree of gravity. However, do we have the ability and the consensus to do that against disparate organizations? Generally we can get space agencies to cooperate, but if anyone looks at the state of the United Nations, it's very rare that they generally reach a common consensus.
Thanks.
I think could I add a little bit to that? So I think the test of whether to do things in space or on Earth is simplify the thing on Earth before you try to do it in space. And so if you need a factory to build something on Earth, and that's the simplest way that you can build it on Earth, then you're going to have to somehow replicate that in space. Or the alternative is to make the thing, the component, on Earth and ship it up there and do the final assembly. So there's just a practical question about where's the best place to to actually do the thinking. Well, that's on Earth, unless you've got an autonomous robot, maybe. And then where to do the sort of the primary manufacture of components, and then where to do the final assembly and the like. So we're going to have to think through the logistics of all that. Now, of course, once we get a long way from Earth, then we'll have to do things in a very different way, but we're a long way from there.
Thank you, Rob. Simon, this is a question for you. It's a crazy idea, apparently, but can we execute what Blue Abyss is doing at a larger scale in an MEO so as to prep astronauts for deep space and outer space missions in space itself?
So when you say MEO, is that medium Earth orbit?
Yes, that's what it means.
Right, thank you.
Yeah.
Well, the key thing that Blue Abyss has at its core is a very large pool, the largest in the world, which is there to replicate some of the aspects of space. So in a sense, there's no need to set up a Blue Abyss in space. The purpose is to actually be able to provide some of the aspects of space on Earth to enable training and preparation and development.
Okay, thank you, Simon. Who is leading in manufacturing for space? Mike?
Probably the United States, unsurprisingly. Mostly the United States, made in space, are predominantly dominating that market, at least for fiber optic and additive manufacturing processes. There's probably no one else realistically who's actually at the level that they're operating at.
Is there support available from the space agencies like European Space Agency?
Yes, there's an ESA Business Growth Network which is about to go live. The first event is in a few weeks' time, and that will be looking at support for manufacturing operations in space, biological, industrial, and others. So yes, and the UK Space Agency has, I think, currently a microgravity call out as well for similar processes.
Thank you, Mike. Can we use portable, universal, fixable, magnetoplasma dynamic thrusters to drive space debris into a space factory placed in a Moyania orbit so as to pick up maximum amount of space debris at a lower apogee on an Earth-centric orbit?
Well done, Sue. That was a mouthful.
Yeah.
Yes, you could, but like most things is, space is small and it's big at the same time. You can spend an awful lot of time trying to drag things from a whole variety of orbits, because if you're going to use a thruster, and it doesn't need to be an EPT or whatever flavor it might be, you've got to get the thruster to the thing in the first place, which means you're going to be expelling energy to get there only to bring it back. And we're not talking, so just as the space station sitting at an orbit of 400 to 500 kilometers, a geostationary spacecraft is sitting at 36,000. We're not talking just a few miles down the road to go and pick up your friend who's happened to broken down. We're talking many, many, potentially thousands of kilometers. So in the scheme of things, it sounds like a good idea. Practicality-wise, I think it's probably unviable.
Thank you. Should we collaborate beyond normal space collaborators? Rob?
Yes.
I would agree with that. I think that's the whole point of this sort of exercise.
Yeah, I would third that. I mean, if your customers for manufacturing on orbit are not outside of the space sector, then you're going to limit your market quite significantly.
I think there's a wider point here. Actually, it's part of EDI. We need to be introducing new ideas into the mix. And when you work within a community, you start to recycle ideas. And so it's essential to actually get out of your normal environments and go and see what's going on in other places. That's why I'm really keen to get more engaged with the space sector to find out what good stuff you're up to, because I want to nick it.
Yeah, and likewise, Rob, I want to nick all the good stuff you're doing in Fusion, because you're learning it the hard way and I want to take the easy lessons.
Sounds like a match made somewhere.
Absolutely, in a sun.
Okay, thank you very much. Is there any major difference in fiber optic production in space compared to that on Earth?
Yes, well, in terms of manufacturing, broadly the process is the same. You have significantly less space on the space station and less power, etc. You have safety as a factor. No one wants to be responsible for setting the space station on fire. But the main difference is ultimately in the result of what you get. The lack of gravitational forces on an optical fiber mean that you get far fewer impurities, which give you the higher performance.
Thank you, Mike. Is there any way that we can produce spare parts for spacecrafts in space directly without interface from Earth?
Well, yes, absolutely, and we're already doing that to an extent. The problem is every spacecraft in orbit, with a few exceptions, is basically your own version of a bespoke sports car. They all come with their own individual trim, different wheel sizes, different engine sizes, and different sized body components. So it's quite hard actually to have a commonality in terms of production of parts. And they use a whole variety of different materials. The aspiration in longer term is to be able to try and get into universal platforms where spacecraft, launch vehicles, etc., start to have commonality in the same way that you can go to Screwfix and buy a selection of bolts, which you can use on anything from your back door to your garden shed.
Just picking up on that a little bit more, we do need to go straight back to productionization of cars back in the early 20th century, where the interchangeability of parts was absolutely fundamental to moving from craft manufacture, as it was called, which is what Mike just described, to mass production. And that process will occur in space as the volume starts to increase and the investment becomes worthwhile.
Thank you very much. I think that's the end of the questions. So I'll hand over to Nick to close out the session. Over to you, Nick.
Okay, thank you very much indeed, everybody. Thank you. Very vigorous question session then, much more vigorous than normal. Excellent. So first of all, thank you very much indeed to Rob and Mike for their excellent talks. Really very good, thank you. And obviously thank you to all of you who joined the session. We obviously appreciate it. One more notice about next week. So next week we have a Orbits 101 or an introduction to Orbits session at 10 o'clock next Tuesday. The link was further up the chat. I put it up in the early stage of the chat right at the beginning of the talk, but you'll also find it in your normal network group, so that'll be well publicized. So please join then if you want, if you're interested, and if you're not and you know somebody who might be, please send them the link. Please register by Monday when we close the books. Okay, thank you very much indeed for everybody. Thank you again, Rob and Mike, and thanks everybody for turning up. Have a good day.